Okay, so our morning speaker today is Vladimir Fock, and he's speaking on Hecke Algebras and higher laminations.
Thank you very much for inviting me here. It's just a pity that I couldn't come. I hoped until the last moment that it's possible. But well, I couldn't. And also I doubted until the last moment what I'm going to speak about, and I'll actually what I'm speaking about is just work in progress, joint with my student Valdo Tatishev. And with my former student, Alexander Thomas. And I am always accused of speaking about some statements which are actually not proven, but that every statement I should start with something like, I have a dream that. This talk will be of this type. So I decided instead of speaking about completely proven statements, I will speak about many conjectures. Well, I tried not to hide that they are actually conjectures, but nevertheless kind of impressed me because they are, well, the related subjects which I had were in different boxes until now. And now they kind of put in the same box. It was impressive. So in particular, laminations and Hecke algebras. Well, just one small recollection of what are laminations and Hecke algebras. So first, what are laminations? For on Riemann surface, on the surface, to the surface. For simplicity, I'll speak about closed surface, but later on open as well. So it's just we have a surface, and lamination is simply a collection of non-oriented curves. So this is a. Sorry, I just pressed something wrong. Sorry. Excuse me, please. It's just a problem with my computer. Well, we have a surface, and lamination to the surface is just a collection of closed curve on it. So you have just non-oriented curves without center intersection. So collection of non-self-intersecting curve, non-intersecting and self-intersecting curves on sigma.
Volodya, sorry, just a question. And they feel the surface, right? There is a curve passing through every point. Is it?
No. Just a collection of curves. Finitely many curves. Find it. I will speak a little bit because, what I'm going to be about, it's a relation over Z.
But do they have to somehow comply with the genus? Like, should there be enough of them, or could they just be one?
No, nothing. For example, empty lamination is also lamination. You have no curves at all. It's just distinguished lamination, which is 0 in this space. on sigma. So this is well, integral lamination, so to say. Now, what are the main why it's interesting to study this space? So first of all, that laminations are related to something. So first thing that the laminations, the space of laminations is just formally is just as discrete. A collection of self-rejection curves, of course, considered up to its isotopy. It's just a combinatorial object. And the main properties of that, well, why are interesting, that are related to different objects. First of all, these are a tropical limit, the space of lamination, the space of laminations, L of sigma is a tropical limit of the character variety. Which is just the space of representations of pi1 of the surface into SO2, SO2. Namely, well, what I mean by tropical limit, I mean, for example, one of the example is that on this space you can have a charts. Well, you can represent the representation space as a recollection, like as a algebraic variety covered with charts with intersection, the space U alpha with the transition function phi alpha beta, and which are algebraic functions, and you can take the tropical limit. Well, you phi alpha beta algebraic functions, they are subtraction free transition functions. And you can replace, therefore, you can formally consider another variety which is given by the same functions, but over tropical semi-ring, for example, over Z. You take Z tropical, so if you take this function over Z tropical, you get, well, if you take it over complex numbers, you get the representation space. If you get, if you replace them by functions over tropical semi-ring Z tropical, then you get elimination space. So this is really, well, it can be interpreted in different ways. For example, the original interpretation by Thurston, who invented the notion of eliminations, was that the infinity of the space of eliminations coincides with the infinity of the space of representations of type mirror space, essentially. So this is a kind of approximation to type mirror space.
Volodya, just a question. So when you say representations in SO2, do you mean this, whatever it is, Teichmüller component or whatever it is?
No,
I mean
the whole thing.
Of pi given by hyperbolic elements, or is it not necessary?
No, I mean the following. So you can take it, well, you have a variety defined by that. So this, well, this is this representation space, which, well, as interpreters say, there is a chart which I can define a variety, which I call another letter by. So if you take its variety over this variety over complex numbers, this is just the origin, this representation space, the character variety. If you take it over the positive real numbers, which are which is also tropical semi-ring, because it's so this is a Teichmüller space of sigma. And if you take it over Z tropical, then you get the lamination space. So just varying the ring over which you consider variety, you consider different geometric objects. One is tropical, one is, well, two in a sense tropical, because positive numbers are also, it's also semi-field. So this is, you cannot subtract. So this is a, this is relation between laminations and all these Hecke space in particular. So it's kind of positive part. So it's a, well, this code is just character variety. This is positive part of character variety, which is Hecke space, and the lamination is tropicalization of now, well, it's not only well, the first thing, this is a limit. Then second, which is also important, this is a kind of duality. So there is a, for every, there is a canonical function pairing between the lamination space and the character variety, which I will denote by chi2 of C. 2 put for SL2, because later on I will need other variety for SLI and for other simple groups. So canonical pairing means you have a function which is take lamination space L of sigma times this variety chi2, well, of, for example, of C, but it's not, it's actually over any semi-field. And you send it to complex numbers. Once again, this field can be any. And the idea is the following: that if you have a just loop, so your lamination is a collection of loops, and this loop is gamma, then you associate to it the trace of the monodromy, trace of if representations, well, we have a representation trace of rho, where rho is just in the representation space. Pi1 of gamma sigma in the SO2. So, and if you have several of them, so you have a product. If you have several loops, gamma I, then you associate a product, gamma 1, gamma n. I do not draw them on the surface, then you associate to it the product of traces for rho of gamma I. So this is a way how one can define a function starting from laminations to complex numbers, and the claim is that this correspondence gives you a basis on the function. So this pairing gives you a basis of functions over on the space chi2, which is a canonical basis in a certain sense. Well, to make it canonical, one should, I put some details into the carpet, because if you have multiple curves, isomorphic curves, you can treat them a little bit differently, but well, it's just technical details. This statement is strictly literally correct. It gives a basis, but a little bit not canonical. Canonical in the sense of Lustig, in particular, for example, the product of two basic elements decomposes with positive integer coefficients, and plenty of other things. So, and the third, this is a, and the finally, the third thing which I would like to mention also about laminations is that, well, I'll switch to the page, sorry. The third is that they are related. So suppose we have, well, there is a way how Thurston considered the lamination. So there is a map from, if you consider cotangent bundle to Teichmüller space, so you have T star of Wittgenstein. So this is Teichmüller space of sigma, the space of complex structure, and you consider cotangent bundle. Then in this space, we can embed as a discrete subset of this space, we can embed the laminations of sigma. And well, if you consider, you can consider also over not only Z tropical, but over Q tropical. And if you consider the lamination space, well, this maybe I should write this way. So if you have a, you can LQ tropical, not L, but chi2, sorry, chi2 of Q tropical, rational numbers with tropical addition, then this embedding is dense. Sorry, maybe I should more
basis on the relations between those Goldman functions for SO2. I think there are probably many relations. I don't quite remember.
Excuse me, could you repeat the question? I didn't hear the end of the question.
You say it gives a basis, but I thought between Goldman, right? You're basically using products, certain products of Goldman functions, but then between Goldman functions, there are relations, or the fact that nothing intersects makes it kind of then there are no relations, or kind of why not the same element would be represented by like many laminations, something like that.
Yeah, exactly what you said, that there is no relation. If there is no intersection, there are no linear relations. Of course, there are multiplicative relations. It's not a set of generators. It's a set of just linear bases. And if you multiply two laminations, then the result is linear combinations of other laminations. Yeah, exactly. The requirement that they do not intersect implies that there are no relations. So yes, there is a map. Well, maybe I should say that there is a map from yeah, well, I would say that there's a maybe better to say that there's a relation between this space and this space, or integers. Well, the lamination space, and I claim the following, that well, suppose we have the cotangent bundle of what is the relation between the lamination space and the cotangent bundle to Teichmüller space. What is the relation between them? What is cotangent bundle to Teichmüller space? This is a pair which consists of complex structure. Element here is complex structure. Plus quadratic differential, which I will denote by mu, but this is a plus quadratic differential. T. And this data define a spectral curve. So spectral curve, which is a double covering of our original curve, spectral curve. Now we have complex curve, spectral curve, which is a Riemann surface of the function. So this is a Riemann surface of square root of t. So square root of t is now it's one differential, but it has two values at every point except zeros. So it gives you so sigma tilde. This is a spectral curve, which is double cover of sigma, and this is the spectral curve is equipped with the square root of t, which is one differential now, just one form. So this square root of t belongs to the h0 of our sigma tilde. And you can take a real part of that, and in this case it will be the H1, sorry. And it will be a real class of homology of H1. And the claim is that, in fact, therefore there is a map from T star to T star of sigma of tau. Sorry, T star of tau. T star of tau to the H1 of sigma tilde and R. And this is local isomorphism. Why local? This is something which, for me, it was a kind of point which is difficult to understand at the beginning. So the idea is the following: that you cannot, in general, you cannot identify all these coverings. So if you vary your quadratic differential a little bit, then you can identify the ramification point move. And locally, of course, if you move a little bit, you can identify the different sigma tildes as just topological surfaces. On the other hand, if you move it, if you change it more important way, then there is no canonical way to identify different coverings. So in fact, the lamination space, which is this map is rather defined if you take a quotient of this space, but by the braid groups, which is just correspond to moving points on the surface. So we consider two-fold covering over the braid quotient by the braid group. In this case, is by the braid group action. And so far it's just correspondence. Now, what is the lamination? So in this, this is local isomorphism. Of course, there are points which correspond to H1 of sigma tilde and H1 of sigma tilde Z. This is the same thing as a lamination over Z. Because if you have H1 of sigma tilde and Z, then you can, so therefore, you can, for example, you have one form on, it corresponds to the one form, which is alpha, which is real part of square root of T. And this, the kernel of alpha is a foliation of your surface sigma tilde. If you forget about orientation of the foliation, then it gives you a foliation of oriented. Foliation of sigma tilde, it's the same thing as non-oriented foliation of sigma, because this foliation, if you take a quotient by the action of the Galois group, will project to sigma, the foliation project to the same lamination with changing of orientation. And if the number of the fact that the homology is over Z. So it means that the number of fibers, well, the number of types of fibers, the topological types of number, well, the fact that it's a Z, alpha is H1 of sigma with values in integers, implies that the, well, I'll maybe draw the number of types of fibers. Fibers is finite. And therefore you can, well, I'll better draw the picture. So you have a surface and you have the following picture that is just foliated by, the surface is foliated by fibers. And there are some fibers which go like that, for example, and there are fibers which go like that, and there are fibers which go like that. Number of types is finite, and you can replace every collection of fibers which are isotropic. You can replace it by one single fiber, but attach to it the integral. So you have the leftmost fiber of the given topological type, the rightmost fiber of given topological type. You replace them by one fiber, but with weight with n fibers. You replace this is just continuous family of fibers. You replace by finitely many fibers, which this number n is equal to the integral of your form alpha over over this path gamma, which is different color. So this is a path which just transversal to these fibers. Path gamma. So this since alpha is an integral class, so this all these integrals will be integer and well the absolute value perhaps. So this is a way how you can, from quadratic differential, you can construct a lamination. This is standard way. For example, there is plenty of activity around that when you compute the volume of lamination space and all this business. So, well, this is one part of the story. So the other part of the story will be the number B, which will be related to Hecke algebras. And before speaking about Hecke algebra, I'll speak a little remark about what is Satake correspondence. Well, maybe I should speak about Hecke algebras before. So I recall that the Hecke algebra the idea is the following: if you have G as a group, well, and I'll for a moment it will be Kac-Motti group. So it's I mean that it could be either a simple group or an affine group, simple or affine. And you have a P, which is a parabolic subgroups in G. Then you can consider we can consider the space of the Hecke algebra H, which depends on G and P, is the space of functions. It's just functions on the double quotient G over P from right and from the left with respect to the convolution. Well, strictly speaking, it's not well defined because the convolution is not, well, everything is non-compact, so the convolution is not defined. But if you consider, so you consider the functions, well, the groups, so they are algebraic groups, you also can consider over any field, and you define the convolution over the groups G and P over a field with finitely many elements, and therefore on the other hand, this quotient itself, well, the convolution, of course, depends on the field which we consider, but the quotient itself. So what's remarkable in this situation, why we really can take the parabolic subgroup and not any other subgroup, that remarks that the G over P from the right and from the left doesn't depend on FQ. So in particular,
is it not like finite in some sense?
Yeah, well, if G is simple, then this is finite, of course.
This is finite set, right?
Because yeah, it's finite set. If it's affine, it's not very finite, but well, what I wanted to say that this is in particular, then if well, G is simple and B is Borel, P is Borel, the smallest one, smallest parabolic, then G over PB from the left and from the right as a set is isomorphic to the Weil group. So it's finite set. Well, strictly speaking, it's true even if it's Kac-Moody. Well, if Kac-Moody as well. So it's even I cannot require that it's simple, but it's not necessary. But the Weil group is, if G is simple, then Weil group is finite. If G is affine, the Weil group is not finite, but it's still the Weil group. So therefore, if P is equal to B, which is kind of the most popular situation, then the Hecke algebra is, or maybe it's better to call them Ivachori Hecke, because it was him who formulated this algebra this way. So Ivachori Hecke algebra is isomorphic to as a vector space is just so H GP GB is isomorphic to the Weil group, isomorphic to the group ring of the Weil group. As a vector space. And well, also the recollection that it's well, everybody knows what is well, the Weil group. So it's given by H of G and P is given by the relations, which is S alpha, where alpha is a simple root, alpha simple roots of G. And for simply laced, I write the relation for simply laced case. You can easily imagine what a relation for other so these are just standard braided relations. So S alpha commute if S alpha S beta commute. If the alpha is beta, C alpha beta is 0, so it means that the Cartan matrix. So they are not connected by an edge of the diagram. So S alpha is beta, S beta S alpha is equal to the standard Braille relation. So S beta S alpha is beta. If C alpha beta is 1, Well, you can write the relations also for a C alpha beta is -1, sorry. If it's larger, and there is another relation which S alpha squared is equal to Q -1 S alpha plus Q, and this relation is additional to the, well, you see that if you consider everything over a field of one element, so Q is 1, Q is the same thing, same Q, which was here the field. So if you consider the field of one element, you get the ordinary Weil group. And if Q is different, so you have a family of, it's actually a family of algebras depending on Q. Well, and finally, well, this is a Hecke algebras, and the another basic ingredient, and it's rather motivational, but nevertheless, I want to well, to share my what I learned recently about
sorry,
that.
Volodya, before we go on, I think maybe I got a bit confused. You said at some point that surprisingly, the Hecke algebra does not depend on Q, but
Not
now
algebras.
in the relation, we see that it does very much depend on Q. So maybe you can share your view on that.
No. Sorry for being. Once again, it's a vector space. It doesn't depend on Q, but as an algebra, it does. So this is just maybe what I said, that something doesn't depend on Q. For example, this quotient, this set, canonically isomorphic for different Qs, or G over P, but the convolution product, of course, depends on Q. And once again, it becomes just ordinary one, then Q equals 1, so which is not. And if you, you also can take a convolution with respect to Euler characteristic, and in this case, it will give you the symmetric, the ordinary Weil group. It's another interpretation of symmetric group as a Hecke algebra. You need to integrate against the Euler characteristic. Well, and finally, well, the one thing which is a Satake correspondence, which I learned recently from the talk of Michael Finkelberg. Following Finkelberg. Which is also, well, apparently not very complicated statement. Well, the proof is definitely not so easy. So we can consider the following two objects. So if G is a simple group, and well, we'll consider G hat as a corresponding affine group. Affine group. So you can, and P is a maximum parabolic. P hat, I will denote in G hat, is maximum parabolic. So, well, maybe it can be made more precise. So G hat is nothing but G over G of well, of series F. Well, I need everything over finite field, so FQ of Laurent series. And in this case, the parabolic is nothing but G of the polynomial. So it's polynomial. It's Laurent loops, and these are Taylor loops. So of G simple, you can construct that, and you can construct therefore the Hecke algebras, which is H of G over P, G hat p hat. And this is an algebra which has, which is infinite dimensional because we are speaking about affine groups. So the while, it's not a while group, it's actually not a subgroup, but a subring of the.
Sorry, can I ask a question? Isn't this the field of Laurent series and the field of Taylor series, as you say?
Yeah.
I mean, right, but then, or the second is the ring, but then the notation is different for Laurent series. No, I mean, you have brackets, curly, round brackets, not.
Sorry, round brackets. Yeah, sorry, maybe.
And then below that is what you wrote there. And below that, I think it's, that is double, but both of them are double.
Double, sorry.
And up there too.
It's Laurent.
Right. And if that's the formal, the bottom one is formal power series, and this one is formal Laurent series.
Laurent. Taylor. Yeah. Right. Okay. Sorry for that. I just, yeah, you are right. So you have H. Well, in this particular case, H is commutative. The observation in this particular case, observation that HGP is commutative. On the other hand, you have you can do the same story, which is actually this is a subgroup subalgebra of H of GB, of course, G hat B hat. Well, B hat, which is the Borel, which is non-commutative, which is as a vector space is isomorphic W hat, which is W hat is a affine while group. Hat just stands every time I write hat, I mean affine version of it. So this is a G simple. Then you can construct, well, something you can forget about the affine part. And this is a, you can take G and quotient it by the conjugation. And you consider the functions of that. So this is functions of G over HG. So, or in other words, I mean just the functions, of G ad invariant. Which ring, which is, of course, you know it very well, this is a character ring, a ring of characters. Well, algebra of characters.
Valeria, there is a question on the chart. What is B hat in the affine example?
In the affine example, B hat is the same, the following thing. So element, I would just, B hat is an element of the, well, it's something like the series A of T, such that A of 0 in ordinary Borel. So this is a kind of halfway. So here I allow any value at 0. And for Borel, I allow only upper triangular values of 0. So it's a finite dimensional difference between the two. So this is a ring of characters, and Satake correspondence. Well, the Satake correspondence isomorphism is the isomorphism actually of these two algebras. So you have functions of G over G, which is the characters of the group, which is very easy thing, which is isomorphic to Hecke algebras of G hat, G hat and P hat.
But don't you have to take Lagrange dual groups?
Of course.
Yeah.
I just wanted to do, but it's strictly speaking not true. But you need to take the Lagrange dual, and this is more or less obvious why you need to do that, because well, that it doesn't work without taking Lagrange dual, because if you take G hat over, well, your algebra W hat is actually an extension of the ordinary Weil group with kernel, which is the set of the R, which is just R is a root lattice. So as a vector space, H of G hat P hat are just functions, well, W invariant functions on R quotiented by W. Well, or on R. So functions on R quotiented by W. And so you have here root lattice, and the characters are functions on the weight lattice. So you need to have, on the left-hand side, you have weight lattice, on the right-hand side, you have root lattice. And in order to have an isomorphism, you need to, well, to change them. So you replace the group with Lagrange dual, which is a natural thing. Or, well, what this is, well, the Hecke algebra has a natural basis, which is, well, there are, in fact, bases in the two spaces. So here, this is a canonical basis, which is, well, H of G hat B hat has a basis, because it's just H of G hat B hat is a space of functional discrete set. So therefore, it has a basis numerated by just the points of the discrete set. H of G hat B hat by G hat B hat from left to right, which is R over W. And sorry, yeah, this is R over W and B hat. And well, you all know that this space has a basis functions on GL over at GL, has a basis by given by the same set numerated by highest weights. So also by R over W. So you have the basis enumerated by the same numbers, and well, the claim is that in fact this isomorphism, well, once again, the isomorphism is an algebras. So as algebras. But this isomorphism doesn't send basis to basis, but there is a transition matrix, which is called Kostka matrix. So there is a Kostka transition matrix. Kostka numbers are just numbers which express one basis and others. But nevertheless, what I want to say, there is a kind of correspondence between well, some discrete object like highest weight of finite dimensional group, enumerate some basis on this set, and the moral of the story is the following: that the R over W. Well, we can now recall that the algebra of functions here are so there is a correspondence between higher weights R over W. In particular, well, one is a consequence R over W, which is and the cells, well, the elements of G over P from the right hand side, from the left and from the right hand side. But this is a finite set, so it corresponds to cells of G hat. Well, if
Volodya,
yeah.
Is it a good point for a break?
Yeah. I'm just trying to say this statement that it was, yeah, exactly. So the moral of the Satake correspondence that you have the some finite discrete set on the left hand side, which is constructed purely out of finite dimensional group, and this finite set gives you the cells on some infinite dimensional object, namely of a finite group. Why cells? Because you have this quotient, so the quotient is discrete set, so therefore it means that the orbits of P's are well, cells in generalized sense, but well, it's product of C's and C stars. So these are these quotients, well, the orbits of P hat from right to give you a decomposition of G hat. And so the cells may be in quotes. So what I am going to do in the second part, I want to explain that in a sense, this Satake correspondence can be put on the Riemann surface, and the role of this discrete set R over W will play by something which, well, I will try to define. It's called higher laminations, and G hat will play. Well, G hat will be replaced by flat connections, by character variety, but corresponding to the affine group, and that's my aim of the talk. Okay, let's make a break now.
Okay, Volodya, thanks a lot.